Good day, students. Welcome to math.serve.com, where we don't just solve, we teach. In this clip, we're going to be going over question number 3 of the 2015 AP Calculus AB free response questions. In this installment, our goal is to go over some tricks, tips, and strategies to help you do well on the upcoming AP Calculus exam. All right, let's take a look at question 3, the A part. It says, Joanna jogs along a straight path. For 0 less than or equal to t less than or equal to 40, Joanna's velocity is given by a differentiable function v. Selected values of v of t, where t is measured in minutes and v of t measured in meters per minute, are given in the table above. So we have the table right here. Part A. Use the data in the table to estimate the value of v prime of 16. Okay, so what is happening here is v prime of 16 is the instantaneous rate of change of velocity, known as the acceleration, at t equals 16. We do not have a function, we have a table of values, so the best thing we can do here is estimate what v prime of 16 is. Okay, so that's what the instructions ask us to do. So this is the approach that we're going to use. Let's look at the formula real quick. So if you have a differentiable function, so let's say if f is differentiable, in this case v is a differentiable function as indicated here, and we have a between a and b, we have c in some interval between a and b, then f prime of c can be approximated using something called the secant line. Okay, so f of b minus f of a divided by b minus a. Okay. Now, this is an equation where calculus basically meets algebra. Here you have a point. Here you're using 2 points. So we have calc here. You have algebra. Now, this is an estimation. The smaller the interval is, as it gets really, really close to where C is located, your estimation here becomes more and more accurate. Okay. So let's go ahead and name these two parts of the equation. F prime of C is the instantaneous rate of change. So I'm going to call that IROC, instantaneous rate of change at t equals c. This is the slope of the tangent line. You can only use calculus to compute the slope at a point. Okay? This equation right here is the average rate of change. Okay, I'm going to call that AROC, average rate of change. And you have to do it over an interval, AB. This equation you have here, f of b minus f of a divided by b minus a, is the same equation as your slope equation, y2 minus y1 divided by x2 minus x1. That's why I call it algebraic. You don't need calculus to calculate the slope of a secant line, but if you want to find the slope at a point, that's what calculus is all about. Okay? All right, so let's go ahead and carry out our calculations. In the context of this problem, the function f of t is our velocity function here. Okay, so we need a, b, so that we can plug it into the velocity function to calculate our average rate of change. Okay, so what is a, what is b? We have the interval given there. We're trying to look for the instantaneous rate of change at 16. Okay, so we want to get as close to 16 as possible. So let's go back to our table. Where is 16? What interval does 16 fall in? 16 falls in between t equals 12 and t equals 20. All right, so these are going to be our a and b values, and this would be f of a and f of b. Okay, so we have ab right here because 16 is somewhere dead in the center. All right, so let's write that down. A is 12 and b is 20. That's our interval. And C, what we're calculating approximating the instantaneous rate of change about is 16. Okay, so now what we're going to do is plug in these values into this equation. So we have V prime of 16 the slope of the tangent line is approximately the slope of the secant line, which is v of 20, v of b minus v of 12, v of a, divided by b minus a. Okay, so that's 20 minus 12. This is kind of related to the mean value theorem, but it's not exactly what the mean value theorem is. Okay, we're just taking advantage of that setup to approximate the slope of our tangent line. In the mean value theorem, we do not have an approximation, we have an equality sign. All right, so it's basically looking for a C where the slope of the secant line is exactly equal to the slope of the tangent line. That's not what we're doing here. We're carrying out an approximation. Okay, so you want to keep those two formulas separate in your mind. Now let's go ahead and use the table to finish this off. V of 20 is 240 minus V of 12, which is 200, divided by 20 minus 12, which is 8. Now, this is a no calculator section. Okay, so if you leave your answer like this and then you put in the units, you get full credit. But if you want to complete your arithmetic computation, you must do it accurately or else you will not get the credit. Okay, so if you want to save time, just leave it like this, put in the units, and you're good to go. But if not, just do it all the way and make sure you do it correctly. Okay, I'm going to do it all the way. 240 minus 200 is 40. 40 divided by 8 is 5. Okay, so the instantaneous rate of change can be approximated using this value right here. This is the approximation of the instantaneous rate of change of the velocity. Okay, now what's the unit here? Well, if you differentiate velocity, what do you get? You get the acceleration, right? Unit for acceleration is distance per time square. The unit of distance here is meters, and the unit of time is minutes square. Okay? Now, what is a cool strategy to determine the units of a given measure if you don't remember what it is? We can always use the formula or whatever equation you calculate in to determine what the unit is. In this case, we have velocity divided by time. Okay? So I can write down the velocity unit is meters per minute. We're told here, meters per minute. Of course, you should know what it is. So meters per minute, and we're dividing that by time. What is the unit of time? Minutes. Okay, so how do we resolve this fraction? Just write these two as fraction over fraction. Multiply the numerator fraction by the reciprocal of the denominator fraction. And you end up with the correct unit, meters per minute square. Okay, so remember, position is distance, velocity is distance per time, and acceleration is distance per time squared. So that's why we have the time right here. Now, using the AP scoring guidelines, for this part of number 3, you get exactly 1 point. All right, let's take a look at the B part. It says, using correct units, explain the meaning of the definite integral from 0 to 40 of the absolute value of v of t dt in the context of the problem. Approximate the value of the definite integral from 0 to 40 of the absolute value of v of t dt using a Wright-Riemann sum with the 4 sub-intervals indicated in the table. Okay, so before we get started with the problem, let's go over some formulas concerning change in position and total distance. So one thing you want to recall is that, firstly, if you're taking the definite integral from a to b of the velocity function as it is, dt, this tells you the change in position. Okay, change in position, or you can think about it as displacement. All right, this is known as a vector quantity. It has both magnitude and direction. Now, what if you were dealing with a definite integral that's similar to what we have in the problem here. The definite integral from a to b of the absolute value of v of t dt. Now, in this case, you're dealing with the total distance. Okay, it doesn't matter if you're going forward or backwards, to the left or to the right. Everything is counted. Okay, this is a scalar quantity because we're not looking at sign. All we care about is size or magnitude. All right. So in this problem, we're going to be working with part 2, which is the total distance. Now, let me go ahead and illustrate the difference between these two for you real quick. What is the difference between total distance or the displacement or change in position? Now, let's say we have a particle moving in a straight line for 5 seconds. Actually, let's say 6 seconds. Okay, so 1, 2, 3, 4. So for 6 seconds, this is the path that the particle traveled in. What it did is it traveled, let's say, 4 meters to the right. Okay, it traveled 4 meters to the right, stopped, and then it traveled 2 meters to the left, relative to the initial position, which is 0. Okay, we're calculating distances from the initial position. So for the time interval for the 60 seconds, the 6 seconds that this particle was moving, what is the total distance and what is the displacement from 0 to 6? Let's do displacement first. Displacement is the vector. Okay, so this is what the displacement is. The displacement is going to basically be 4. That will be positive because you're going to the right, plus, since you backed up 2 units, let me make this a little bit, make this correct. So we went back 2 meters, okay? And then since you backed up 2 meters, that will be 4 plus negative 2, okay? And that will give us a displacement or change in position of 2 meters from the original position. That's kind of like what part 1 is talking about. Now, what about the total distance? Total distance. Now, the total distance doesn't keep track of sign. Everything is positive, so to speak. So you go 4 units to the right, 4 plus, going back 4 units. So in order to make sure that we're not considering the sign, we can just basically take the absolute value, okay? So absolute value of that plus, going back 2 units, you take the absolute value of negative 2. All right, and then this becomes 4 plus 2, which is 6. All right, so you see the difference between displacement and total distance. This is the total distance right here going all the way to 4 and then backtracking. Displacement, on the other hand, is how far did you go from the original position? Down. There goes your displacement. So that's basically the difference between these two. Okay, so we are asked to explain the meaning of the integral, definite integral from 0 to 40 of the absolute value of v of t dt in the context of this problem. So this is basically the what? Total distance that Joanna travels from 0 to 40 minutes. Okay, so this definite integral is the total distance that Joanna jogs in meters. Okay, that's the unit for distance in meters from 0 less than or equal to t, less than or equal to 40. What's the unit of time? Minutes. All right, so this is the meaning of what this integral expression is saying. Okay, so using the scoring guidelines, just writing this explanation correctly with the units, you earn yourself 1 point. This problem, you earn a total of 3 points. Okay, you get the other 2 points by doing the second part of the problem, which is approximating the value of the definite integral using your right rectangle approximation. So we're to approximate what this is, the integral from 0 to 40 of the absolute value of v of t dt. What is this? Equal to, we're supposed to approximate it using right rectangle approximation involving 4 subintervals. Okay, before we do that, let's review the formula real quick. All right, so let's say you wanted to find the right rectangle approximation of 4 subintervals starting from x1 all the way to x5. What is that going to be? Well, that is the width of the first rectangle times f of x2 plus the width of the second rectangle times f of x3 plus the width of the third rectangle times f of x4 plus the width of the fourth rectangle times f of x5. Okay, so whenever you're doing the right rectangle approximation, you're taking all points to the right of the left endpoint. So that's why I went from x2 all the way to x3. Okay, so let me give you a visual on how to do this. Now, whenever you're doing rectangle approximation problems, the first thing you always want to do to help you organize your intervals is to draw a visual. Give yourself a well-labeled visual, okay? So let's say this is our time span right here. We're going from x1 to x5. So let's say this is x1, 1, 2, 3, x2, x3, x4, and x5. Okay, now what does the right rectangle approximation look like? Well, first of all, we need to know what our widths are. Okay, so the widths that I was talking about here are basically how long the separation is. So from here to here, that's W1, this is W2, W3, W4. For RRAM, MRAM, LRAM, the width doesn't change, okay? You always use the width exactly as it is. You kind of use it for trapezoidal approximation, but in that case, that is basically the height of the trapezoid, okay? So you have these widths. Now, to find the area of the first rectangle, you're going to use the right of the left endpoint. So you start from x2, use x3, x4, and x5, okay? So your first height, the height of your first rectangle, that is going to be f of what? That's going to be f of f of x2. Okay. Now the area of the first rectangle is going to be the first width times f of x2, as you can see here. And then how about the next one? To do the next one, you're going to just proceed to x3, x4, and x5. So that would be a2. A2 is f of x3, so we have this height right here. F of x3 times the width 2, that will give you what a2 is, which is the term we have right here. And then you just follow that pattern to get all the 4 subintervals that are needed for this problem. Now, when you're creating your rectangles, you don't have to draw it to scale. It's the value that actually matters. But if you want to draw it to scale, that's fine also. Okay, so that is f of x5, the fourth height of the fourth rectangle, so f of x5. And then if you multiply that by W4, that will give you the area of the fourth rectangle. Okay, so this is A3 and this is A4. So this is just a formula. When you're doing this on the AP exam, of course, you want to apply the formula directly to the problem. Okay, so let's go ahead and do that right now. So we have 5 subintervals, so this is how you will solve the problem. You start by drawing a number line. Let's see, 1, and then we're going to partition it. It's not drawn to scale, okay? You don't want to be too stuck on drawing it perfectly. It's the way that's labeled that actually matters. So let's see, we have 12, 1, 2, 12. Just copying the values from the table. 20. Obviously, it's not drawn to scale, okay, because the sub intervals have different widths. Okay, so this is our x1, x2, x3, x4, x5. We want to find out what the widths are. So this is W1, W2, W3, and W4, the width of the fourth rectangle. Okay, so W1 is 12, W2 is 20 minus 12 is 8. Just subtract the numbers. W3 is 4, 24 minus 20. W4 is 40 minus 24 is 16. So you have your widths. Now you're going to find the height of each rectangle and then multiply them by the corresponding widths to get the area. So since we're doing the right rectangle approximation, you're picking all the points to the right of the left endpoint. So you ignore 0. This is not factored into the calculations. If you're doing LRAM, you ignore 40 and pick all the points to the left. Okay, so let's figure out the height of the first rectangle. This is going to be, the function here is the velocity, so we're going to have velocity v of 12. Okay, but since we're calculating the total distance, not displacement, or change in position, we have to append that, add the absolute value component to it. Okay, so that's the first height, A1. And then the second height, you can guess what that's going to be. Absolute value of V of 20. So the second height is going to be the absolute value of V of 20. Multiply that by this width to get A2. And then we have the third height and the fourth height. Okay, so let me just draw that in. So we have the third height and then the fourth height. You don't have to draw it to scale. This is just setting up the problem so we can accurately apply the formula. That's what it's all about. You don't have time to sketch a perfect graph. You're not asked to do that here. We're just computing what the value of the rectangle approximation is. Okay. All right, so there you have it. So this is A3 and this is A4. So what is the right rectangle approximation? Using 4 intervals from 0 all the way to 40. So it's basically A1 plus A2 plus A3 plus A4. Okay, so let's write it down. A1 plus A2 plus A3 plus A4. Right? So what's the area of the first rectangle? First rectangle is the width, which is 12 times the height. Absolute value of V of 12 plus A2. The width is 8 times the height. Absolute value of V of 20 plus A3. The height of, the width of 4 times absolute value of V of 24. That's the height. And then plus A4. The width is 16 times the absolute value of the height, V of 40. Okay, this absolute value component only plays a role whenever if you happen to have a negative output, which is the case in this problem. Okay, all right, so let's go ahead and finish this up. We have 12 times V of 12 is 200 plus 8 times V of 20, which is 240, plus 4 times 20 V of 24, which is 220. All this I'm doing using the table that is provided. Now the V of 3, V of 24 is a negative answer, okay? But when you take the absolute value, what happens? It becomes positive. So this is actually where if you don't apply the absolute value, you get your answer wrong because of this piece right here, okay? And then the last part is 16 times V of 40, which is 150. Now, on the AP exam, if you go this far, you express it as this. You put your units on, that's perfect, you get full credit. But if you want to simplify your arithmetic expression further, you must do it correctly or else you're going to lose your points. Okay, so if you want to save time, just box this answer and you're good to go. All right, but if you want to proceed, make sure you proceed with care. Make sure you do everything correct. Okay, so I'm going to go ahead and finish off the entire problem. So we have that plus 8 times 240 is 1920, plus 4 times 220 is 880, and then the last one is 2400. And then when you add everything up, you end up with 7,600. And what's the unit here? We're calculating total distance, so this is in meters. All right, so remember, when you end up with this arithmetic expression, you can box it, put the units on there, and you earn your full credit, okay? For this problem, you earn, for this part of problem 3, you earn 2 points. Okay, so let me write down a final remark. The total distance traveled 0 to 40 of the absolute value of v of t dt is approximately, it's an approximation, 7,600 meters. That is your final answer. And a good practice to do when you're taking the AP exam is to box your final answers. I didn't do that in the other part, but always box your answers because it really helps the grader to understand your result. All right, let's take a look at the C part. It says, Bob is riding his bicycle along the same path. For 0 less than or equal to t less than or equal to 10, Bob's velocity is modeled by this function right here, where t is measured in minutes and b of t is measured in meters per minute. Find Bob's acceleration at t equals 5. Okay, so one thing you want to note for the FRQ on the AP Calculus exam, a lot of the parts are not related to the previous part. Sometimes they are, a lot of times not. This question has nothing to do with Joanna. Okay, so this is an entirely different problem. What we're looking for here is acceleration. What is the connection between velocity and acceleration? So you always want to remember your position, velocity, acceleration, and jerk continuum, x vag. Okay, when you're going down, you differentiate with respect to time, and when you're going up, you integrate with t. All right, in this problem, we are going from velocity to acceleration. What's the connection here? How do you go from a velocity function to the acceleration function? You differentiate, okay? So since what we're doing is differentiating, what the problem is asking us to do in essence is to find b prime of 5. That's what we're doing. Whenever you're finding the velocity at a point, you always have two parts, okay? One thing you want to remember is that you do your calculus before arithmetic. So the calculus component comes by finding the derivative of the velocity function. And then secondly, that's where the arithmetic component comes to play. You evaluate your derivative at the specified point. A lot of students substitute before they differentiate and then they end up with 0 or some other wrong answers, but that's not how you do it. You differentiate before you evaluate, okay? So let's do it. Part 1, let's find b prime of t. Now, b of t is the velocity function given by t to the third minus 6t squared plus 300. The derivative of that, b prime of t, we're going to be using the power rule here, term by term differentiation, okay? So when you differentiate t to the third using the power rule, you power down the power, t to the third, and you mark down the power by 1, 2. Same goes here, you already have a 6 factor that out, power down the power, times 2, mark down the power by 1, 2 minus 1 is 1. And then the derivative of a constant is 0. Your acceleration function, b prime of t, is 3t squared minus 12t. We're done with part 1. The second part is to evaluate. Okay, so evaluate the derivative at t equals 5. So to do that, that's pretty straightforward. We just simply plug in 5 into our acceleration function. B prime of 5 is equal to 3 times 5 squared minus 12 times 5. So we have 5 squared is 25 times 3, 75 minus 12 times 5, which is 60. And now you have 15. Unit of acceleration is distance per time square, so it's meters for the distance per minute square for the time. Okay, let's box our final answer. Now for this question on using the AP scoring guidelines, you earn a total of 2 points. The first point is for part 1, finding the derivative correctly, and the second point is in evaluating the derivative at the specified time, t equals 5. All right, let's take a look at the D part. It says, based on the model B from part C, find Bob's average velocity during the interval 0 less than or equal to t less than or equal to 10. Okay, so there's something you want to be really careful about. All right, this is one of the common mistakes that students make when calculating the average of a function. Okay, so what students do is, they say, the average of the function over an interval is the function evaluated at the right end plus the function evaluated at the left end or the lower interval divided by 2, just like you do in statistics. You just average the values. This is absolutely wrong. Okay, so you want to watch out for this common mistake concerning the average value of a function. Looking for average velocity, this is the correct formula that I would like you to recall, which is that the average value of a function is basically the length of the interval, b minus a. You're dividing the entire area by the length of the interval. Okay, so you just basically think about the area as something that can be transformed into a rectangle. If you transform your area into a rectangle and you divide the area by the width, what are you left with? You're left with the height. That's what the average value is. Okay, so you take 1 over b minus a times the integral from a to b times f of x dx. Think about it as area divided by width. All right, area divided by width, which basically gives you the height. That's what this formula is saying. Okay, so we are going to be applying this formula to this scenario. In this case, f, the function, is our velocity function. Okay, so f of t is b of t, which is t to the third minus 6t squared plus 300. Okay, our lower bound is 0, and our upper bound b is 10. Okay, so if you can recall the correct formula, this is now assessing your ability to apply the fundamental theorem of calculus part 1 accurately. All right, so b average is going to be 1 over b minus a, 10 minus 0, as indicated here, times the integral from 0 to 10 of the velocity function, which is t to the third, minus 6t squared plus 300 dt. Okay, if you set up this equation correctly, by accurately applying the average of a function formula, you earn yourself 1 point. Okay, now to earn the next point, you have to accurately find the antiderivative of this function right here. So you're going to have 1 over 10. Now we're going to use the power rule again, term by term integration. We're going to have t to the fourth over 4 minus 6t to the third over 3 plus 300. You just add the t on there to it. Okay, this is evaluated from 0 to 10. So if you can accurately integrate this function right here and set it up in this format, put in the limits of integration, this result earns you the second point for this problem. Okay, so this is another 1 point. To get the third point, you just have to accurately apply FTC part 1. Okay, so you want to be really smart here. There's a lot of room for mistake with FTC1. You do not have to compute it completely to earn full credit. Okay, so if you do the following, check this out. If you say, oh, this is 1/10 times, plug in the upper limit into all your t's. So you have 10 to the 4th over 4 minus 6 times 10 to the 3rd over over 3. I could divide this and make that 2, but that's okay. Plus 300 times 10. And then for the evaluation of the integrand at the lower limit, what you find out is they all have t's as a factor, right? So if you plug in t into all of them, what happens? They all become 0, minus 0. Now, if you stop here, guess what? You get your third point. But if you want to proceed, you must proceed with caution. You have to get the final answer right, or else you lose your calculus point over an arithmetic mistake. Okay, so it's left for you to determine how you want to proceed. My advice to you is just stop right here, box the answer, call it a day, and get your full credit. Okay, but I'm going to go ahead and finish the problem off so I can show you exactly what the final numerical result is. So we have, let's see, 1/10 times, now 10 to the 4th, it's just simply 10,000. 4 zeros over 4 minus 3 goes here, 1, 3 goes here, 2. And then 10 to the 3rd is 1,000 times 2, which is 2,000. Plus 300 times 10 is 3,000. Now I'm going to find the tenth of everything here, okay? If I do that, I'm going to have 1,000 over 4 minus 200 plus 300, okay? And then when I simplify that further, 1,000 over 4 is simply 250, right? 250 minus 200 plus 300 is positive 150. I'm sorry, positive 100. And we add these two together, you have 350. And this is average velocity. Okay, what's the unit of velocity? Distance per time. The unit of distance in this problem is meters. The unit of time in this problem is minutes. So 350 meters per minute is your final result. Remember, you could box the answer right here and get full credit, or you can, if you want to waste your time and go all the way and then just put it here. Remember, if you want to stop in the unsimplified arithmetic format, do not forget to add the units. Although it doesn't call for units here, but it's always good practice to always add the units, so that in the event that it asks for units, you're already in the pattern of putting down units. So in this place or this place, wherever you stop, you earned exactly 1 point. Remember, this is a timed exam, so you want to make good use of your time. You don't want to waste your time on one problem, doing arithmetic simplifications when you should be working on other problems. Thanks so much for taking the time to watch this presentation. We appreciate it. If you found the contents of this tutorial beneficial to you, do give us a thumbs up. The feedback you give to us is greatly appreciated. If you have any questions, just post your questions in the comment section below, and we'll be glad to assist you at our earliest convenience. Do not forget to subscribe to our channel so you can get updates to other cool calculus tutorials such as this. More clips can be found on math.serve.com under AP Calculus. Thanks for watching and have a wonderful day.